it short, and then we can have more discussions after the break. Okay, just some in response to some questions that were asked. This one, so this is topologically true. I mean, positive real locus are true. I feel that because I'm giving a few talks, I'm allowed to start a new job. It's an empowering privilege. So this one is a positive real locus are true, and for this one we cut off. We cut off at this one. Now I also want to maybe if there's a way I can draw this where you will recognize something that you've seen before. So let me do that right now. So here is t x plus y plus 1x y plus 1. So t is positive, and maybe not too large. And then this is the amoeba component, or this is a compact bit of amoeba component. So if you complain, I'm drawing this in, I'm drawing the locus here. If you want to do the amoeba, you need to what you effectively would be doing is you would be looking at t times e to the r plus e to the s plus 1 over e r plus s equals 1, where now your r and s would be real. So you can do both pictures. Doesn't matter. Yeah. And now, so this, so this integral here, omega t. So it's actually the claim is that this is omega t. Gamma t. Thank you. You know what I'm about to say. I've been saying it all week. I'm not going to say it again. People haven't learned. Yeah. So this is the same as an area of that thing. But after Merriman. That's it. After Merriman.
So did you see the blue part?
I think the answer to that is yes. It is a bit outside my area of expertise, so I'm going to claim yes. I think yes. And the way you should think about this, so if you integrate over this one, this is the integral of you integrate with boundary in big W t 1 minus 1. But the one we want to do is here you integrate with boundary in little omega minus 1. And so this mirror map is this transformation for this one to this one. Maybe at this point I can just make a few comments, which is something you can prove. That's right. So big W. Maybe I can. Yeah. Let me find some little corners in the board where I can tell you this. Maybe here. So let's just remove this. So we have a.
Can we see that in one more?
You don't need to, right? because it's going to be so incredibly clear that I don't need to lower the dimension for you. So we have a C star squared inside here, which is and then WT restricted to that C star squared is equal to T x plus y plus 1 over x. Right? So that's why I wrote here this equation. Now, but now comes an interesting bit, which is that if we look at locally, or analytically locally, this is where all this analytification comes in. Analytically locally, near the so this is near the large. Oh, near that. I'm just gonna like so. This is a large complex structure limit for the family of ellipticals. Well, but right now we just fix some T. We have this rational elliptic vibration, and by the way we don't include this. We don't include this. So the claim is that analytically, locally near that thing, we can write. So W is a coordinate, is a global coordinate, and remember I did the tape curve. This is like the tape curve, right? So here this is like tape. There was a reason I did the tape curve, and it was so that when I say this, you're not too confused. So we can write that WT, little w is equal to W 1. Can you guess the next one? Plus 2 T W cubed plus 6 to the W6 plus 32 to W9 plus 6. So this expression here is the Aganagichwapa open mirror map. So it's a thing we've seen in the work like Conan, Chan. That's right. Open mirror map. Yeah, exactly. So we see this in new papers with Popeye and Sicho. Yeah, it shows up in different places. So this mirror, this open mirror map shows up, and I should say this is. I can reprove this to you. So this was originally proven by Goddard and Grefnitz and Zaslow. Maybe Grefnitz, Goddard and Zaslow. This was extended by Fenelon, high dimensions. But anyways, this, yeah. But I can prove this for you very quickly if you want. I can reprove this, and maybe now is a good time to just do that if you want. And the proof will make evident it will make evident how canonical coordinates are useful. Okay, so this integral, let me finish my comment that I was making. So this integral being equal to, so this equal to the twist gamma times j function, gamma hat times j function of ky, or that shows up in Iritani and et al. It's a like no symmetric gamma conjecture. What he shows is if the gamma conjecture is true for P2, then the gamma conjecture is true for local P2, and you're computing this area in terms of something that depends on the gamma plus and the j function. I mean, he writes it using the I function, but you can coordinate change. Then there's also a statement where you the length. I'm getting a bit sidetracked, but like the length of this related to the periods of I function. Anyways, there's also a statement for this, which is the gamma cap j function of the hyperspace. Yeah, and so these are statements that, if you remember what I wrote last time about I functions, j functions, you kind of, there's a natural context. But also this, using the intrinsic measure symmetry kind of takes care of coordinates for you. If you look at your Candice paper, there's a lot of confusion about coordinates. Doing intrinsic measure symmetry takes care of coordinates. Let me prove this for you, if you like. Let me prove this, and then we'll go to. So, can you guess? Having said what I said, can you guess what corresponds to this one? This one. And then this change here is, as I said, there's many ways of thinking about it. For example, by mirror map. And then this one corresponds to some mirror family. And then the relationship between this and this is quantum state. So quantum set. So last time I talked about something called quantum deficits, but actually I was talking about quantum set. I just used to go in words. This is very embarrassing. This is the statement of quantum set. C1 log t. I just put 1. So if I take the j function of y comma d or local p2, I could replace this by k of y. It introduces some signs and some factors, but then that thing is equal to the j function of t, c1 log of some transformation q of t. I put z equals 1 because I really need it. And then that q, and then that q of t, I can say something about that q of t, but that's quantum set. It's a statement that you take the j function of d, plug in some coordinate change q of t, and you get the derivative of the j function of local, which is the same as the j function of local.
What sense is this?
Good question. I think that the idea is you're looking at O minus v versus section of O of v. I don't know if that helps. so right, so ky, that would be the whole space. So I'm not quite, I don't know, that's, so this is a Arnold's paper from and so my kind of mean claim is that, well, 20 years later you can prove this in like 3 lines, which is you take, I kind of, last time I showed you a statement about I functions, which was easy to prove, and then if you just keep track of the mirror maps, you get that statement. And I guess you have to say, what is this? It works quite easy. We're always smart 20 years later. Okay, so one more time, we have 3 different inputs, which leads to 3 different families, and they're all related by a change of variable. This one and this one is related by this change of variable here. You can kind of guess what this change of variable is because the j function of d is trivial, so that helps you to guess what it should be. But we can also write it down later. And then the change between these two is given by the this kind of open mirror map. And I can prove this to you. Yeah, let me quickly prove this to you, and then we'll say something more about the construction. And yeah, this and maybe we have this like very nice description, which maybe I'll comment about. So define y of t via so we set w to be 1. So this is where this is a so we want to set little w. You remember little w was this like local analytic comment. Set it to be 1. And we look at the expression of the slope potential near infinity. And then you can show that yt cubed is I'm going to use some fancy words. So Mahler measure of so inverse of Mahler measure of 1 over t minus x plus y plus 1 over xy. So, well, this is just using some fancy words to like make you feel like I'm talking about something very complicated. But it's also which is also the same as this kind of classical period. This one is the same as the classical period. The reason I'm writing it this way because you get modular forms, which is something you get a lot when you do Mahler measures. So it's kind of in a different, interesting direction than what I'm doing. Classical period, which is some interval of 1 over 1 minus wt1. With some, you take some, omega. So this is, you take some xyz vibration, you integrate, this expression. But in any case, you could just show that this is, so, and then you can show that this is equal to log t cubed plus some 1 over k greater than 1 to the parallel 3k t to the 3k. So this uses either of those uses Johnson. Because this expression, these are the constant coefficient of W. So this classical period will only, you can compute, it's going to be given by, you just take the expansion and then you'll have, if you compute what it is, so it's actually sorry, so it's not quite a quantum, it's not quite a classical period, that's why I wrote inverse of the Mahler measure, because this 1 over k comes from, because you're taking the Mahler measure base. So this is, what is this? You integrate log of 1 over t minus x plus y plus 1 over xy, omega along, and 1 over 2 pi I, and maybe minus 1. So this is what it is. And then that will really depend on the constant coefficient, and then because you use a result by Johnston that tells you that you can compute the constant coefficients I anywhere you want in your your constant coefficient are given by some broken line calculation, which you can do anywhere you want, and you get the same expression. That's how you get this one. And now, this implies that, this implies that, so this implies that the inverse, this implies that yt cube is, sorry, now so there's an exponential here. Sorry, and it's, I changed my notation. T cube divided by 1 plus t. Yeah, so there's an exponential here, sorry, and then you can use this to figure out that this expression, which is then gives you exactly this term. So let me say this one more time. You just define a new function using this trick up there. Then you compute an expression, which is the inverse of the Mahler measure. This only depends on the constant coefficients of W. So this, you can take out the log, then you have log of t cubed. Sorry, exponential of log of t cubed, and then plus sum of constant coefficients, which should make exactly so. Here you can, you really compute when you take the power series expansion. And then again, we want to use the fact that we want to invert this relationship. We need to use the fact that so we have this relationship. That means that if you take the inverse, we will get this relationship. Sorry, W1 take inverse. Okay, so that. Maybe like super convinced, but if you just do this carefully, it really becomes like a few lines proof if you use the fact that these constant coefficients of the multiplication of open lines are the same. Yeah, I don't see lots of the light. So let's just go back to our construction and to give you the final. We can do it in more detail. Any questions at this point? Okay, so let me tell you something about IMS, how it works, and about how our works. So, okay, no. So, no. Remember, I wrote down what, okay. So, there will be a part of the work where you have to calculate the. So that will be a consequence of the construction. So this will be consequence of the construction, and then what we did here is we were looking at the expression of this near infinity. And near infinity, we know that we have some coordinate little w and t, and then you use this fact about the broken line calculation, and we're using that. We're using the fact that. Sorry, this was a y word. Sorry, thanks. Where this thing comes from the construction. We evaluate this near infinity. We write this expression that I did. And then we compute some other coordinate. And we show that these things are the same using the multiplication by broken lines. And then we deduce that whatever inverse is going to give us a right. Maybe we can, if you want, we can do it like again in more detail. But maybe let me now get to why we get this expression. Something kind of nice about the construction is that you get this kind of like nice expression. So step 3. So from YE, we need to build sigma 1, which is this is the tropicalization. This is an integral affine manifold. With singularities. So the way it works is if you have a stratum, so if let me do first the picture, and then I'll give you a bit more details. So we have this, degenerate fiber, and then we have this vertical fiber. And we have here, this one is Y. We have Y, so this is E, D. Here this is D that generates, and then we have D1, D2, D3. And so to tropicalize, we replace every component of the divisor with like a ray. So we'll be like a ray like this, and then there'll be three rays. So every EI, every component of D gives us a ray. And then and also because we have a map down to A1, and there's log structure at 0, we also get a map to the tropicalization A1. So to the picture, the following. So we have one, this is a ray that corresponds to, we call this one E. So one that corresponds to E, E blue. And then we have 1, 2, 3. It corresponds to E1 wool, E2 wool, E3 wool. We also also have this map down to the array corresponding to A1 family. And the 5 over 1, or it's map G, looks like this. We have a triangle and we have faces and going 1, 2. Result, so that G minus 1 is this triangle, C is 0, and then we attach to it this one, this one, this one, and this one. Doesn't matter. But we have, and these are I'm taking. So this is the take the complex, polyhedral complex generated by the base. So we have one component vertical and then three central components. So we'll have so this is the face that's generated by these three things, and then we intersect at one at distance 1, and then each of these is the one which is generated by the vertical one and two of these. We intersect at distance 1. So more kind of intrinsically is if the stratum of D is given as spec C tau integral dual. We add tau. We add the cone tau. So if locally, because we need things to be locally toric, which they are. So if you take a stratum of these intersections and divisors, where the local equation of the divisor is given by spec of some cone, sorry, spec of some so this is a strictly convex. This is a strictly convex polyhedral cone. We add this, and if we have so if this is the stratum y0 tau, and if we have an inclusion of stratum, of strata, then we add an inclusion of cones. The good thing about this is also this determines an integral affine structure. So this determines, determines an integral affine structure, meaning all of these cones have a lattice by construction. The dual has monomerism. Another way you could describe it is you could say that you take the cone of Cartier divisors that are supported on locally variable strata. And then the outcome of this is the outcome is so we have plus some lattice points. So here here when I drew it this way, so I glued the cones using the recipe, which was given here, right? So if you have an inclusion of strata, then I use the inclusion of cones. And this depended, the exact shape depends on resolution of x bar 0. So y bar 0 was 3 components, but we had to introduce some singularities. And if you do this kind of symmetric resolution, this is what it looks like, meaning that if I have an integral tangent vector here, or basis of integral tangent vectors, I can just move it around like this. But you can see that if I was here and then I move it around here, then here there's a cut. Here there's a cut. There's a cut. So maybe I should say the gluing of cones is modeled after geometry. Example. So this is V1, V2, V3. This is maybe the law of A2 in well, it doesn't matter. It's like minus something like that. And let's say this is minus 1, minus 1. This is 1, 0. This is 0, 1. And the divisor corresponding to, we have a relationship that tells us that the divisor corresponding to V1 plus divisor corresponding to V3 plus divisor corresponding to V2 is 0 if you put the intersection of the square. And so that tells you how to do this cone. So these are 3 different divisors, where we have V1 or V3, V1, V2. And we'll know how to glue them together using this rule. So this is a rule. So we're applying this to also. But we have some. But that gives us some similarities, which are the 4-dimension 2 strata. And so we need there's some monodromy as we go around there. So there's so another local picture we like is to instead of writing it this way, we kind of break it up. We break it up and pull it out. So this was that was a description. So this is the description. So this is this sigma 0 in the construction. Sigma 0 in the construction gives you formal spec of x plus minus 1, y plus minus 1 inside xt, which is which is given by this lattice, and so we're just using toric construction. We have a polytope, and that gives us. So we have a moment polytope that those are local. They give us local coordinates for some chart. And then you can compute. So we have theta functions, theta. Theta corresponding to E. Here is this E. If you compute this on this torus, inequality for this expression. And the reason is you have to look at broken lines, and the broken lines have to come from this direction. And you're evaluating them here, and you find that, well, the only way you can kind of come here is to do some, like there's a little bit of bending that's going on, but you can only bend one time. And if you bend one time, then this bending will give you come from, there's like an algorithm that tells you that it has to look like this, where this carries an x, this carries a y, this carries a mod of xy. But because you cross this wall, you get this extra. You can see looks of acceleration. There's also there's also an image right near infinity. So this is a chart, asymptotic chart. Now, if you go far away, and here there's we have an asymptotic chart that shows like this. So this was sigma 0, we removed sigma 0, and we made it so the gluing of these, they have the same equivalent structure, but if you pass from here to the other side, they're similar. So okay, let me try to wrap it up. So there's step 4 is a wall structure. So step 4 is a wall structure, and this is given by counts of punctured maps to the family. So we have puncture map to the whole family. So because this is one dimension high, you could really have actually puncture invariants, and you do. They give you disks. But there's a key fact, which is that after set t to the k plus 1 to be 0, so you do something like formal thickening, then there's a region, so away from some k, so here we have some compact bit k, so but away from k, away from k compact, all the walls, all walls are horizontal, and carry as wall crossing functions. Basically the ND, but with specified wall type. So there was a point where we talked about wall types. Okay, so at this point I need to talk about some results. So there's some magnets did describe description of the wall structure. That's the type of wall structure. Wall structure, CPS, Carl Pumper Siebert, just scattering diagrams for this. There's work by Pierrick, square, well, not Pierrick, but Pierrick and Pierrick, so linked to the stability manifold of K2. So this picture shows up, there's a scattering diagram, and the scattering diagram shows up as a scattering diagram where you vary the space of single functions of K2. And then you get some correspondences between invariance for local K2 and invariance here. And it particularly improves the projective representation. But in any case, now the point is that this asymptotic wall structure is really is parallel, and then we can use this use to parameterize gamma t, and then calculus gives us the theory. So one way you can think about this is as follows. We start with our degeneration. We construct this integral affine manifold with singularities. We endow it with a wall structure. So this is like a geometric. This wall structure acts a bit like a geometric generating function. It's like a geometric generating function. So we have a generating function which is not just a power series, but it's supported on some integral affine manifold. Yeah. And now this integral will like very carefully pick out some relevant part of this wall structure. And thanks to this correspondence, we know that invariants that occur are very similar to the invariants we get. So we can parameterize this and we can just compute. So we don't wait. And no computation is needed. So no computation. What I mean is no fancy computation. We didn't have to solve some period integrals. We didn't have to, or something. Sorry, we didn't have to solve some complex equations. We really just have some cycle. We parameterize it. We integrate. And then we have good question. That's an excellent question. You're paying attention. So this is a way to think about this. So your question is about how are these two related, and the answer is extra gluing data. So this arrow here. So IMS for YD versus IMS for Y embedded. This is, by the way, in CPS. This is the difference is gluing data. Let me explain. So, in both cases, the construction works the same way. Sorry, I should have said, E versus this one. But that's equivalent. So the difference is in gluing data. So when you run this construction, if you did it just for the elliptic curve, which is equivalent because you still get this one parameter counting, you have this wall structure that tells you how to move, right? Okay. Do you remember when we did the Tate curve? The Tate curve, it was something like C star to the Q to the Z. Right? And now it should be Q to the like 3Z. That's how it takes place. That's what you get from this construction. There's no corrections. Okay. Now, but when we do this, when we introduce this embedding, when we go from the wall structure of the pair to the wall structure, so we quotient out to the wall structure of the elliptic curve. I had this picture, remember, where it decomposes into three pieces. So the thing is, what happens here is that these walls become gluing data. So now the integral, before the gluing data, you just length, length, length. So the length is 3. But now you have to like subdivide your computation of the integral into like pieces, and then when you have these like local charts, and you go from one chart to the other, you have this like extra parameters. So you have some extra equations that tell you that if you write down a chart here and a chart here, they will differ by something like uv equals this Walker's equation equals f, which is the Walker's equation. And so your parameterization has to like incorporate this. And then these Ewing functions are the same as the ones that came from here. That's why you have this Ewing data. Now, maybe your question is about what about okay? So your question was about so that's how you made this one and this one. Okay. But because all 3 families are the same, that then tells you how these different things are related. Let me try to say this one more time. But let me draw another picture that's going to be helpful. So we have the big W plane. We have the little W plane. So the little W plane, it only makes sense kind of asymptotically, yeah? So we have the positive real locus here. And here this makes sense everywhere. Here, you know, we're probably, yeah. And then we have, but we also have the Q plane, where Q is so Q is the intrinsic parameter for canonical or mirror to so here we also have so now the fibers are all the same, but they have different parameterizations. Now, if you go from this parameterization to this one, you get this quantum set business. If you go from here to here, you have this. I mean, so maybe this is going to help. So there's a result in CPS. Maybe this is what you're asking. There's a result in CPS which tells you that WT, little w, is equal to W of 1 plus some n 1 3 e minus 1. I think that's maybe a 3e minus 1. 1 plus some minus 1 t to the 3e divided by w to the 3e where these are two-pointed log pairs. This is maybe CPS, maybe also interactive as well. So there's some extensions like so here we're looking at counting curves that meet the divisor in one point tangency 1 and one point tangency 3d minus 1. And this expression is a statement that if you evaluate the superpotential here, then like far to infinity, then you have one broken line that comes from here, because we're really far. But then you can have other broken lines that come and they like turn around and they come back. Yeah. And the combination of all the possibilities gives you this expression. But now you could still kind of, so you could do a change of coordinate between those two. Yeah. And this is maybe what you're asking about. I mean, you have to do some. So this thing is equal to. So then, okay. So you start with this expression, and then you do this little argument that I gave you. And you can show that this is the same as the open mirror map. And then you can do various, like you can like, going from here to here gives you like modular forms. From here to here gives you invariants, and then you can like split it up into 2 steps to get this smaller measure and other periods. And yeah, I mean, anyways. So we have 3 different parameters that correspond to 3 B-model canonical parameters that correspond to 3 A-model parameters. And is there different directions? I don't know if that's it. Yeah, maybe these things take time. Maybe I